Hello students, welcome back. In section 1, we reviewed exponential and logarithmic functions and their properties, including exponential and logarithmic rules. And in section 2, which is an optional section, we went through some examples of exponential and logarithmic equations. Now, the main body is section 3, exponential and logarithmic models. This too is partly a review. I take it back. This too is a review from algebra classes. Still, it's modeling, so let's do this again. Okay, let's consider several different types of models. First, compound interest model. Compound interest model looks like this. Suppose that you invest a principal P with annual interest rate R compounded n times a year. Then the balance after t years under this discrete compounding scheme is like this. Now, n times a year. Most of the time, if you purchase an investment CD with fixed interest rate, it will be compounded 4 times a year, quarterly compounding. So n is equal to 4. But sometimes it is compounded monthly, so n is 12. Theoretically, you can consider n equals to 2 semi-annual or n equals to 1, but those are rare in reality. And then, of course, this is a math course, so you can consider n equals to 20 or 100 or 365 daily compounding. We can consider things like those, even though we don't really do that in real-life situation. Now, yeah, okay. And then a sketch of proof is kind of like this. Let's see, at time 0, nothing was earned, so we stay at P. Okay? If you plug in t equals to 0, then 0 power. So the whole thing is 1, so it's P. Okay? Now, one compounding period later, so that is 1 over n years later. That is 1/12 of a year for monthly compounding, 1/4 of a year for quarterly compounding, and so on. So 1 over n, previous balance times the interest. Makes sense, right? Previous balance, and then it grew a little bit. But what's the interest? Well, interest rate times the principal, but interest rate R is annual interest. So if you're going to do this for quarterly reinvesting, then it should be R divided by 4. If it is going to be monthly reinvesting, it should be R over 12, and so on. In general, R over n. So factoring P out, we get P times 1 over R over n. That's one compounding period later. Say 1 quarter later or 1 month later. Let's do this again. Next compounding period later, this amount of money times and plus the interest. Okay, this is a previous balance, okay? So previous balance is this, and then interest. So that money times interest rate of R over n. Again, R is annual interest rate. So for quarterly compounding, I have to multiply R over 4. For monthly compounding, R over 12, kind of like that. So R over n is the interest rate for that compounding period. And then let's do some algebra. Factor P times 1 over P times R over n out. Then everything is out here, so it's going to be 1, so 1, and then R over n. So 1 plus R over n. Wait a minute, we have the same thing here, so that thing's squared. That is my balance after the second compounding period, like second quarter or second month. Let's do this just one more time. Now, after third compounding period, previous bound, this is previous balance, okay? And then I have to add the interest. This one, plus the interest rate, R over n, times the same money, previous balance. Okay, that's the previous balance. That plus this times the interest rate. Again, the same thing, factor this one out, so everything is out, so what's left is 1. And then here, r over n. And then there's second power already, so we have third power. See the pattern? Fourth power, sixth power, fifth power, sixth power, seventh power, all the way up to the very last, n times t. So if it is t years later, then it's n times t compounding period later. So 10 years later is equivalent to 120 months later or 40 quarters later, depending upon what kind of compounding you do. And that's how we get the formula. Sketch of proof, okay, except for proving the pattern is indeed this pattern. We got all the proofs there. Now, what if you take continuous compounding? That is theoretically possible, but not in reality. But theoretically, it's possible, so let's consider it. So limit n goes to infinity. So we compound infinitely many times, or compounding period is getting closer to 0. So we get this limit, and then 1 plus r over n and t. And then you see, I want same r over n over here, or reciprocal of it, because you see, this thing, let me copy and paste this thing. And then in order to avoid confusion, let's change the character. That's formula number E. Now here, in this case, this m is what? N over r. So I can change this into 1 and then n over r. And then n over r over there. So that's m. So that's e, and e to the rt power. So we have continuous compounding. So exponential function comes as a limiting case of compound interest model. So it's a good way to explain exponential function or the natural exponential function in math classroom, but in reality, people do not use continuous compounding. This thing exists only in math room. Let's see. Let's do an example problem. The amount of money resulting from investing a principal P for time t years at an annual interest rate R compounded n times a year can be expressed as follows. All right. Okay, $1,000 is invested at 5% interest rate for 7 years compounded. Once a year, 4 times a year, 12 times a year, and then daily, 365 times a year. So n values are 1, 4, 12, and 365. All right, same formula, different n values, and run your computation. So you'll have to punch into calculator 4 times. If you do it right, you're going to get this for compounding once a year, this for 4 times a year, this for 12 times a year, and this for 365 times a year. And then this thing does not grow on forever. As you saw before, continuous compounding becomes an exponential function. So it grows here, gets bigger and bigger and bigger, but it doesn't it doesn't go all the way to infinity. It stops here. Anyway, this was just a computation problem. How many years later will the initial investment double its value if the interest is compounded yearly, quarterly, monthly, daily? So you have to set this one equal to twice of P. And then solve that equation. So that's equal to 2P, and then n is 1. So that's the equation. And n is 4, there goes the equation. N is 12, there goes the equation. N is 365, there goes the equation. And solving those using logarithm and some computation are as follows. You see, in order to kill off this, take the logarithm, and then t comes out as coefficient, and the log of 1.05, that's just a number you can divide out. And then same thing, same thing, same thing. So what do you get? 14.2 years for annual, the once a year compounding, 13.95 years for compounding quarterly, 13.89 years for monthly compounding, and 13.86 for daily compounding. So if you compound more often, then money will grow more quickly, but not infinitely quickly. It'll stop at exponential of RT, the continuous, continuous compounding case, this one. Okay, all right, some computation problem we did. Now, do you have enough time for other examples? I guess not, so let's stop here. So much for compound interest model. And as you can see, money grows rather quickly. So compound interest, if you understand, you must earn it. So invest your money. If you don't understand, you end up paying it by taking debt. I think it was Albert Einstein who said it. Compound interest. Those who understand earn it. Those who don't, pay it. Don't pay the compound interest. Don't get into debt.